Okay, we're talking about more types of bonds. Lesson one, we were introduced to ionic, which is when one or more atom loses an electron and another atom gains an electron. Then we had metallic bonds where they just share their electrons in that electron C model that we saw. Now we're going to be talking about covalent bonds, which is a very common type of bond where electrons are shared. So the first thing is defining what is a covalent bond. So again, um, these are non-ionic, whereas ionic ones give and take electrons, covalent ones share electrons. Important. Um, a molecule is when you have different types of atoms bonded covalently. So don't confuse a molecule and a compound. I know sometimes in common language we use them interchangeably, but a compound is when you have more than one type of atom bonded, right? But if you have two different atoms, they could be two different atoms of the same element, so like two nitrogen atoms, they are bonded covalently, they are a molecule. So some examples of diatomic molecules, diatomic just means that there are two atoms bonded together covalently because they're molecules. These are things that don't necessarily exist by themselves in nature because it's more stable for them to be in pairs of two. So things like oxygen, hydrogen. Remember when we were talking about this, when we were talking about like the composition of the air, and we noticed that hydrogen was like H2. Um, this is why, because it's more stable for these to exist as diatomic molecules as opposed to by themselves. So how single covalent bonds work. So, a little recap. I'm going to show you here an ionic bond. I'm going to go back to table salt because that's like the simplest one that we're all familiar with. So, I have a sodium with one valence electron and a chlorine with seven, right? And I'm doing my Lewis dot structure to show those valence electrons, which is just another way of saying outer electrons in case you forgot. And what's going to happen is this guy is going to just give that electron over there so that they both have 8. Because sodium on its next lowest shell would have had 8. And now chlorine has 8. With covalent bonds, they don't have that same makeup where they can just like give and take one. So what they'll do is share so that both have what they need. So, for example, here, I'm going to get rid of that. We have, wrong thing. For example, here, we are looking at a diatomic molecule of hydrogen. Now, hydrogen doesn't need 8 total. It's an exception, hydrogen and helium, because they're so small. They only have that one shell. They only need 2 to fill it. But it's the same idea if it were 8, and I'm going to show you one with 8 as well. But we're going to start with hydrogen. Since they both need 2 to be full and each of them has 1, instead of this hydrogen just giving that away, and so one would have 2 and then the other one would have 0, they say, hey, well, I have 1, you have 1, we can share them, kind of like the metallic bonds do, and now both of us have 2. That is how covalent bonds work. We call it a single covalent bond when there's only one pair of electrons being shared. See, one pair there. This is a single covalent bond. You could also represent this as a line like this. You'll learn more about these structural formulas when you get to chemistry, but there are just multiple ways of representing a single covalent bond. Here's a single covalent bond that doesn't include hydrogen, which is our exception that only needs 2. Oxygen needs 8, like most of our other atoms do. But they only have 6 electrons because it's in group 16. So what we could do, since this guy has 6 valence electrons, and it's water, so it's bonding with hydrogens. This hydrogen has 1, and this hydrogen has 1. So they can share these. So now This hydrogen has the 2 that it needs, this has the 2 that it needs, and this oxygen has the 8 that it needs, that most of our atoms needs. This is another way of drawing this. Remember, you can represent a single covalent bond with a line as well. So, because there are only 2 electrons being shared here, these are single covalent bonds. Now, a sigma bond, a vocab word, you'll hear more about in chemistry, but this is when you have a pair of electrons being shared at the center. So it's a single bond, essentially. And it's combining 2 different atoms with only 2 electrons. So what we just saw with the oxygen and the hydrogen, that was sigma bonds. Also, if you were to have methane like this, each of those are sigma bonds. They are one pair of electron in the center of those 2 atoms, combining the 2 of them. That's a sigma bond. This is a lot of words you don't need to write down. That's just showing you an example of what a problem would look like if you were asked to draw a Lewis structure. So patterns on glass can be made by chemically etching its surface with hydrogen fluoride. Draw the Lewis structure for hydrogen fluoride. So this over here is the question. This is the response. So first thing you need to do is figure out how many electrons each one has. So you're going to find these on a periodic table. I know that hydrogen is in group 1. I also know that fluorine is a halogen, which means it's in group 17, which means it's going to have 7 valence electrons, right? Now, if this were an ionic bond, we would go ahead and take that electron from hydrogen and give it to fluorine. However, this is not an ionic bond because these are both nonmetals. Covalent bonds are typically going to happen between nonmetals. Ionic bonds are typically going to happen between a metal and a nonmetal. But also it used the term molecule. So you know that these are covalently bonded, which means instead of taking one, they're going to share these 2. So you could represent it with a line like this. This over here just showed you the actual bonding, the chemical reaction with the different structures. So then we can also have multiple covalent bonds, meaning that there are more than just 2 electrons being shared. If you have 2 pairs, meaning 4 electrons, you get a double bond. If you have 3 pairs, meaning 6 electrons, you get a triple bond. Now, this can happen if you have to bond to different things that one single bond won't give them enough electrons. For example, let's look at this oxygen here. So, again, we have 6 electrons on each of them, right? If they each were to share just one pair, these 2 right here, now each of them has 1, 2, 3, 4, 5, 6, 7. Not enough. They each need 8. So they can each share another pair, and now they each have 8. That is how we get double bonds. This is a neater way of drawing that. Same idea with triple bonds. These 2 nitrogens here, if you were to just share one pair of electrons, they wouldn't have had the 8 they need. So you needed to go to the point where you were sharing 6 electrons for them to each have 8 electrons they can use. Now, this diagram down here at the bottom, this is chemistry stuff. You don't necessarily need to decode this yet. But what you do need to know is what a pi bond is. So sigma bonds, remember, were the ones right in the middle that connected those 2 atoms. Pi bonds are all the ones you add after that first sigma bond. So, for example, you have here a double bond between these 2 carbons. One of those would have been a sigma bond, the first one there. The next one would have been a pi bond. Same thing with if I had nitrogens like this. The sigma bond would have been in the middle, and the 2 other ones would have been pi bonds. So the first line that connects them first pair of electrons, technically, is a sigma bond. Any additional bonds are pi bonds. Now we're going to talk about electronegativity. You do not need to copy down this table. You do not need to memorize these numbers. I'm going to explain something to you using this diagram. What you do need to know is what electronegativity is. Electronegativity and electron affinity, pretty much they mean the same thing. It's just one has to do with when you're bonding and one is just when the element's by itself. But it's the same idea. It's the tendency of an atom to want to accept an electron. So from what we've learned so far, these guys over here tend to be the ones that really want to take electrons, really want to give electrons, which is why the numbers over here to the right are much higher than the numbers on the left, because these guys have a higher electronegativity. If there's a bond, more of the electrons are going to come from these guys on the right. All right? So electronegativity is important when we're trying to determine something called polarity of a bond. We'll talk about here in a second. But the thing I want you to understand is, what is electronegativity? Tendency of attracting electrons, and know where are the most electronegative atoms on the periodic table, the elements to the right over here, because they have more electrons already, so they want to take them so they can get closer to that. Also not a chart you need to memorize, but one you need to understand. This tells you what type of bonds you'll most likely have based on the difference in electronegativity. So, for example, something on the right, like chlorine, that's extremely electronegative, you would take that number and subtract it with what it's bonded with, like magnesium, and the difference between those two numbers will tell you if it's an ionic bond, if it's a polar covalent bond, which we'll talk about what that is in a second. If it's mostly covalent, meaning between polar and nonpolar, but definitely not ionic. And then a nonpolar covalent bond will have zero difference. And we'll talk about what polar and nonpolar covalent bonds are here in a second. Here's an example of what we just were talking about. You take the electronegativity of chlorine, which is 3.16, the electronegativity of hydrogen, and subtract them. There is a difference here of 0.96, which is going to tell you that you have a polar bond here. What a polar bond means is, think of poles, right? Like on a magnet, you have a positive and a negative. If you have a way of splitting the positive and negative side of a molecule or a compound, then it's going to be polar. Ionic compounds are very polar because one side's going to be more positive than the other. That's why one's taking electrons and one's gaining. When it comes to covalent bonds, though, it can be a little more tricky when they're sharing electrons. But we know that the chlorine over here is going to end up with 8, and the hydrogen's only going to end up with 2, meaning 8 negative charges is a lot more negative than 2 negative charges. So this side of our molecule is going to be a lot more negative, and this side is going to be a lot more positive, making a positive and negative side. Those are your poles. This is a polar molecule. Okay, so we have covalently bonded things that are polar or nonpolar. Nonpolar molecules are not attracted to electric fields. Remember, electric fields have charge, right? Negative charges. So if you have a positive side of a molecule, it's going to align with an electrical field because it's pretty much charged. It's like it has a positive and a negative side that can attract to a negative field. If you are completely neutral all the way around, you're not going to attract an electric field. Now, here's an example of two molecules. I'm not going to draw all the dots. I'm going to just draw the structural formula. That's what this is called when I just draw the bonds without all the other dots. And we're trying to figure out if these are polar or nonpolar. Well, we're going to end up with 8 electrons around there, 2 around here, meaning this side is going to be a lot more negative than this side. So that is a polar molecule. Now, these guys here are all going to have 8 around them. So there's going to be an 8 here, 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 and here. Now, there's also a difference in electronegativity. Chlorine obviously wants to take more electrons than carbon does. So there's going to be a slightly more negative side by the chlorines than by the carbon. However, because it's balanced all the way around, they kind of cancel out. So this would be nonpolar. That's also not how you spell nonpolar. There you go. These are just another 3 common examples. 2 of them we just saw of things that are polar and nonpolar. Water is going to be extremely polar, which is why it dissolves so many things. It's a great solvent because it has such a positive and negative side that positive and negative side can kind of pull at the positive and negative side of any other substance that tries to dissolve in it. We just talked about this molecule here and why, even though it's more negative around the chlorines, it balances out. And then here we have ammonia, which can be divided here into a positive and a negative side, so that is polar. So some other things about covalent bonds. Solubility is ability to dissolve in something. We talked about this when we talked about solutions. Polar molecules in ionic substances are typically soluble because they have that positive and negative side that make them easy to pull apart if there's a positive and negative side of another molecule. Nonpolar ones are much harder to dissolve. They need a nonpolar substance to dissolve them. All right, and we're going to stop with a couple properties of covalent compounds. So they have weak forces, so they have low melting points, low boiling points. They can be solids. They can also have the lattice that we saw in the metallic and the ionic compounds. They're going to be a lot softer. And there's less attraction between different molecules. So within a molecule, they can be strong, but between one molecule or the other, it's weaker. So covalent bonds, there's a lot more to it. They're slightly more complicated than the ionic and the metallic, but you can do it. Take some time. Look at the videos I have attached there for you. That is lesson 13.2.